Okay, so we are starting a new unit, right triangle trig. So today we're just going to kind of review radicals, right triangles, Pythagorean theorem, and simplifying radicals. Okay, so let's go ahead. I'm just going to share my screen. All right. So when we're looking at a square root, that's what we call this little house-like thing. And it's also, you'll hear me refer to it as a radical. So the radical is actually that shape, and then the radicand. So let me write this down. Here's my radical, and this is my radicand. Okay. So if we have this radicand, if that happens to be like, let's say, x squared, right? Then x is going to be what we call the square root of that number. So when I think about it, I'm just going to draw myself a little square. You know that in a square, the side lengths are the exact same, and we find the area is just x squared. Okay, so I multiply them together. If I have the area, but I need to find out what the side lengths are of that square, we take the square root. Right? So in this case, we're trying to think of the two numbers that multiply together to give me 64. Well, the positive root would be positive 8, and then negative would be the negative root. Okay, so usually when we have a square root symbol, there's two roots. There's a positive root and a negative root. In geometry, majority of the time we are just looking at the positive root because a lot of times we're using this to solve a distance or a length or a measure. And most of the time we are always measuring, usually distance is always going to be positive. Okay, so majority of the time we are going to be using the positive root, but just realize that there are going to be negative roots that can come into play. So this is an example of a perfect square. A perfect square is something that when we take the square root, we get an integer, not a non-decimal number, right? We get like a whole number. So that's what we call a perfect square. And when I think about the perfect squares, you can kind of figure out what they are just by thinking about, well, if my sides of my square, and then what would that area be? So if my sides are 1, the area is 1. Well, 1's not a pretty useless perfect square. So usually the one that we like to use for the smallest one, it would be a side length of 2. So 4 is my smallest perfect square. If my side lengths are 3, the area would be 9, and the square root of 9 is 3, right? Then we can continue. 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared, 64, 9 squared, 81, 10 squared, 100, 11 squared, 121, 12 squared, 144, 13 squared, 169, and let's see, 14 is always the one that I forget about. 14 squared, I think it's 196. Okay. And then 15 squared is 225. I'm kind of running out of room here. But this kind of continues on and on and on, just goes indefinitely. I generally would tell students you really should be pretty familiar with these numbers. 196, that's the one I always forget about. But that will come in handy. The more you are familiar with these perfect squares, it makes it a lot easier when we are simplifying a radical. So when we are looking for exact answers, we will usually leave things in radical form. Sometimes they might ask you to like find the square root of 52. So like notice 52 is not a perfect square because it's somewhere between 49 and 64. So if I were trying to estimate the square root of 52, I would imagine it's going to be 7 point something. Okay, so if I put in square root of 52, I get 7.2111. Now notice that the exact answer, because this decimal goes on forever and ever, it's irrational. It doesn't end. It's non-terminating. So this is a more exact term. So it kind of depends on how you're asking. In a lot of upper math, we're going to want exact answers. And so we're going to leave things as a simplified radical. So the easiest way to do this I find is if you are familiar with your perfect squares and you're familiar with factors, if you can figure out the largest perfect square that goes into 52, and then find the other factor. So this is why it's helpful to have all these perfect squares. So obviously I can figure out where does 52 fall on the list. And then I'm going to look and see, are any of these a factor? Do they divide into 52 evenly? 49 doesn't, 36, no, 25 is no, because it's 2 times 26. 16, no. Usually for even numbers, I try 16. You always want the largest one. So like 16 doesn't, because 16 times 3 is 48. 9 doesn't go in because 9 times 6 is 54. So 4 goes into 52. And let's see, 4 goes into 5, 1, that's 13 times. Okay, so this is what this breaks down into. And I know that 4 times 13, I just kind of wrote them as separate radicals. When that happens, when you're multiplying radicals together, the radicands get multiplied together. So I could have just rewritten this as 4 times 13 all underneath the same radical. I like to start with perfect square first because I can take the square root of 4. It's 2. I cannot take the square root of 13. It's not a perfect square. So I leave it underneath the radical. And so that is the simplified version of square root of 52. All right, so I've got a couple common ones here. So 45, 45, hopefully you recognize that 9 and 5 make up 45. Those are factors. So 9 and 5. The square root of 9, it's a perfect square. That's 3. I cannot take the square root of 5, so it stays under the radical. So 3 times the square root of 5. This is a simplified version of the square root of 45. Okay. Square root of 32. Sometimes you get students that will say 4 and 8. Then you always have to look at that other radical. But I like to start with the largest one. Okay. So 32 is somewhere here. So 25 does not go in. Wait, 16 goes into 32. 16 and 2. If you came up with a smaller radical, you just have more work to do later. So this square root of 16 is 4. I can't take the square root of 2, so I leave it under the radical. If by chance, let's say you had just tried to do 4 and 8. Okay, let's say you said 4 and 8. And then you'd get 2 times the root of 8. And you'd say, wait a second, 4 goes into 8 as well. So I then have to bring this is all being multiplied. So I have to rewrite this again. 8 is 4 times 2. So now I have 2 times 2 times the root of 2. And then that's where that 4 times the root of 2 is. So you notice I've done this twice. This is definitely a little bit more time consuming, but if you're stuck on things, you can always try 4 and then look and see what's left over and try 4 again. It's that's more guess and check. So the more familiar you are with your factors and times tables, the easier this becomes. All right. So this one, again, this is the same thing. We're really looking at simplifying the radical of 28. Once we simplify it, we have to multiply that 3 kind of out front like how we did here. So let's look at this one. 28, all right, so 28 is between 25 and 36. 25 doesn't go in, 16 doesn't go in, 9 does not go in. Okay, so the only one that goes into 28 is 4. If I don't have any perfect square factors, then it's simplified as it is. But 4 goes into 28 7 times. And I need to bring down that 3 as well. Notice I'm just bringing everything down and I'm just rewriting 28 as square root of 4 times 7. I can take the square root of 4. It's 2. And then now anything that's outside the radical can be multiplied together. So 3 times 2 is 6 times the root of 7. Okay, why this might come in handy is when we're starting to do things later on and you're finding exact values, it gets easier and easier to simplify things. And usually, in upper math, you're going to want to use exact values. So we're going to be shying away from decimals a lot. Okay, so let's look at just some fundamentals with multiplying radicals. We kind of have already gone through this. Because anything that is outside the radicals gets multiplied together, anything inside the radicals gets multiplied together. And then we might have to simplify the product, okay? I usually like to do the multiplication first, unless I have a perfect square. I'd like to do the multiplication first and then simplify. So for example, here, this is like the square root of 3 times 12. So this is the square root of 36. Oh, that's a perfect square. So we're going to call that 6. So square root of 3 times square root of 12 just ended up being 6. And that was a lot easier to do than to try and simplify this one. And that's more work for yourself. Okay, so on this one, outside the radical is 2. There's not a number other than like an invisible 1. So really, 2 stays outside the radical. And then this is going to be 6 times 3. I can't simplify these as they are, but when I multiply them together, I get 18. Now here's a perfect example. This is not simplified because now 18 has a perfect square factor. It's 9 and 2. So square root of 9, square root of 2. I'm going to bring that down. And now this is 2 times 3 times the root of 2. So that's 6 times the root of 2. Okay, so this now became this. Again, outside the radicals, so 4 times 6, that's 24. Inside the radicals, I can't simplify anything the way it is right now. So that's just 50. But now I can. Can you see what perfect square goes into it? Let's look back up here. 25 and 2. The more you practice with these, the more easier it becomes. So this is 24 outside the radical. 50 breaks up to 25 and 2, and they're underneath the radical. Square root, the reason we pick 25 and 2 is because this is a perfect square. It wouldn't make sense to pick 10 and 5 because I can't simplify those. 25 and 2. So this is 5. And that 2 stays underneath the radical. Now, 24 times 5 is 120. And then that is my simplified term. Okay. Last but not least, this is when we're squaring something. So this really is the same thing as saying this. Okay. And so square the outside, square the radical. When I square a radical, 5 square root of 5 squared, they undo each other. A square root and a square cancel each other out. Or if we think about this, this would be 5 times 5, that's 25. It's a perfect square. So this is really like 4 times the root of 25, or what we end up seeing is that it's 4 times 5, which equals 20. Okay. A lot of times people will forget about the fact that this also needs to be squared, right? So just kind of visualize that one when you're doing this. Okay. So it's a good stopping point for right now.